This next problem is a bit of a classic, and I've actually gotten multiple requests to do some variation of this problem. So it says, find the volume of the largest open box that can be made from a piece of cardboard 24 inches square. So let me draw my piece of cardboard. That's not, I don't want to draw it filled in. So my piece of cardboard it's going to be a square. I'll draw it pretty big because I want you to visualize it. And it's 24, what did they say? 24 inches square. So it is 24 by 24. Square by cutting equal squares from the corners and turning up the sides. So what are they saying? Well, they're saying we're going to cut equal squares from the corner. So let's say we cut and let me see if I can draw this well. So I'm going to cut a square here. And I'm going to cut an equal size square there. I want to draw this neatly. And then cut an equal size square there. And then cut an equal size square there. Right there. So I'm going to cut out those corners. And then I'm going to fold up the sides. Right? Just so you can visualize it. So those dotted lines are where I would actually fold the box. And then I would end up with an open box. And let's see what the dimensions would be. And that's actually what the whole crux of the problem is. So how big of a squares should I cut out in order to maximize the volume of the box? Well, these are equal-sided squares that I'm cutting out. So let's say that each side is x. So if this is x, then this is x, 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 this is x. And then what is going to be the volume of our box that when we fold up everything? So let me see. So I'll draw the base. So this dotted square right here, that's going to be the base, right? I'll draw it at an angle. That's the base. And what are the dimensions of the base? Well, this base is going to be the length of this side of the cardboard minus this x, right? So this base right here, that is going to be 24 minus 2x, right? It's just the whole length minus this minus that. That's how long that is. And of course, this is going to be the same length. This is going to be that same length. All of these sides of the base are 24 minus 2x. So it's 24 minus 2x. And then this side is also 24 minus 2x. And then what is going to be the height of this open box that we're creating? So let me draw the sides of it. And it's open, which means it doesn't have a top to it. Right? So we have an opening here, so you can kind of see the inside of the box. And what is this height? Well, when you fold these flaps up, the height is x. Right? If you can think about it, this side here, this is really just a bit of visualization. This side right here, that you can view as this thing right here. I can even do it in a different color for you. You can view this side, this front-facing side, as this right here. I'll just do a couple. I don't have to do all of the sides, I don't think. You could view this side as this side right here, right? It's folded up, and then this back side is this back side, and that side there is that, and this is the base. Anyway, so that is the volume of our open box, and we want to maximize it. So how do we do that? Well, let's write the volume as a function of x, and then take its derivative, figure out where the derivative is 0, and hope that that's a maximum point. And we'll prove it by taking the second derivative and seeing. Now we actually want it to be concave downwards, because concave downwards looks like that. So that means you found a maximum point. So we know that the volume as a function of x, I like writing the big V's. The volume as a function of x is that side times, you could view it as depth times length times height. So it's x, the height, times the depth, 24 minus 2x, times the width, 24 minus 2x. Now let's see if I can multiply this out. This is probably the hardest part about this problem. So x times, what's 24 times 24? I want to say it's 4. Well, it's kind of sad, but I've made so many careless mistakes recently that I don't want to make any more, and I want to get the right number. So 4 times 4 is 16. 4 times 2 is 8, 96, 0. 2 times 24 is 48. 9 plus 8 is 17. 576. That's what I thought it was. I should have memorized my times tables up to 25. But anyway, 24 times 24 is 576. 576. And then we'll have 2 times 24, so that's 48x, but we have them twice. So it's minus 96x, right? Because 2x times 24, minus 2x times 24, and then minus 2x times 24. So it's 48 to plus 48, so minus 96x. And then finally the last two plus 4x squared. 4x squared. And now we can multiply the x's out, and we get the volume of the open box is, let me put the x term first, 4x to the third, I'm just multiplying this out, minus 96x squared plus 576x. Let me erase this. I should have been able to do that in my head. But anyway, I'm not too proud to show that I didn't know that. Let's see. So let me erase that. Let me erase that. And so, what do we want to do? We want to take the derivative of this, figure out at what value, x values do we have a zero slope, and then test to see if those are maximum or minimum points. And if we have a maximum point at that x value, and if it's a global maximum, then we have found the x value that optimizes the volume. And you might want to graph these and experiment with them and get a more intuitive sense of it. But that's really what we did when we found minima and maxima, and we did concave upwards and downwards and all of that. So anyway, what the derivative v prime of x is equal to 12x squared. This part's the fun part. 12x squared minus, was it 180, 192 x plus 576. Plus 5, that says 576. I know it's hard to read. It's hard to read for me. So let's figure out where this equals 0. So we want to know where 12x squared minus 192x plus 576 is equal to 0. And the easiest thing to do here is just to divide the whole thing by 12 both sides, because when you divide 0 by 12, you still get 0. So you get x squared minus, what's 192 divided by 12? Well, 192 was 24 times 4, right? It was 24 times 4 is what is that right? 24? No, 24 times, oh no, I just took it too. 24 times 16 is 192, right? I just want to I've been making so many careless mistakes. 12 goes into 192, 1, 12, 72, right, 16. I should have been able to, anyway, minus 16x plus, well, this was 24 times 24. So this is also, this should be 12 times 48. So this should be plus 48 is equal to 0. And we could, right, 24 times 24 is 576. So 12 times 48, right. So now we just have to factor this. So what two numbers that when I add them, I get minus 16, and then when I multiply them, I get 48, positive 48. Let's see, 6 times, let me make sure I did this. So 12 goes into 72 6 times. I just want to make sure I have the numbers right. As you can tell, I don't do these problems ahead of time, because I want you to see that I go through the pain as you do. So let me make sure 12 goes into 576. 12 goes into 576, what, 4 times? 48, and you get 96. 12 goes into 90, right, 48 times. 12 goes, I shouldn't have had to do that. But I've been making so many careless mistakes. I haven't eaten dinner yet. So anyway, maybe I'm just missing the easy factor, right? Because I have, what numbers? You get 12 times 4. Oh, actually, I just figured it out. 12 times 4. Sometimes when your brain is in calculus mode, the algebra 2 gets difficult. So this is the same thing as x minus 4 times x minus 12 is equal to 0. So at x is equal to 4, we're at some type of minima or maxima. We're at some critical point, and at x is equal to 12. Now let me tell you something. We don't even have to look at the second derivative here. What happens when x is equal to 12? What will happen to the volume of the box? If x is equal to 12, what is the length of this base? It's 0, right? Because the length of this base is 24 minus 2x. So this would be 0, this would be 0. So this is a point where we have a volume of 0. So you know that this is going to be a minimum point. And if you want to verify it, take the second derivative of the volume and evaluate the second derivative of the volume at 12, and you will realize that we are concave upwards and that x equals 12 is a minimum point. So you already know, in all probability, the answer is x equals 4. And if you really wanted to verify it, you could take the second derivative at x equals 4 and make sure that we are concave downward at that point, right? Because if we want a maximum point, we want to be someplace where the graph looks something like that. So we're at a maximum point. So what's the second derivative? V prime prime of x is equal to 24 x minus 192. And what's 24 times 4? It's 96, right? So v prime prime of 4 is equal to 96, right? 4 times 24 minus 192, which equals minus 96. So the second derivative at this point is negative, which means that we are concave downwards, which means that this is a maximum point. And once again, I challenge you to find another value of x where you get a larger volume. And just to get an intuition, how large will this box be? Well, if x is 4, then each side is 24 minus 8. This would be 16 by 16 by 4. So that would be the optimal volume for that box. Hope you found that useful, and I will see you in the next video where I will do another optimization problem. And this one is especially fun. See you soon.